This is Chapter 9, Section 1, Solutions. A solution is a term that refers to a homogeneous mixture between two substances, two or more substances. And this term homogeneous means that it looks uniform. Okay? The different components of the mixture are uniformly dispersed or distributed throughout one another, so you can't really see which parts are one substance and which parts are the other. In a lot of cases, a solution or a homogeneous mixture will appear to be a pure substance until you analyze it a little bit further. Now, a solution, or most solutions, consist of one substance that's in a smaller amount, and that's called the solute, and then another substance that's in a larger amount that's said to dissolve the solute, and that larger substance is called the solvent. So these are the two parts of a solution. The solute is dissolved in the solvent. So again, the solute is the component of a solution that is present in smaller amounts, and the solute is said to dissolve into the solvent. The solvent is there in larger amounts. And because it's homogeneous, the solute spreads uniformly throughout the entire solution. Okay? And it's also not visible. You won't see particles of solute in a true solution. You won't see cloudiness or milkiness, because those are both indications that you have large particles scattering light in a certain way. So you won't see that. It'll be a clear solution, transparent solution that you can see through. But it may have a color, because even individual molecules of certain compounds can absorb certain wavelengths of light and allow other wavelengths through, and so they'll give the solution a certain color. But you won't see the particles themselves. The whole solution will just look like it has this uniform color. The solute and the solvent can also come from any state of matter, solid, liquid, or gas. But in solution, they're considered to be a distinct physical state. So once those particles actually get dissolved and now they're being surrounded by solution, or solvent molecules, I should say, then they behave differently than they would in the solid, liquid, or gas phase. And so sometimes we give them a different phase designation. In particular, if they're in a water solution, we say that this is the aqueous phase, and we give it the designation AQ. Okay, so if you see AQ, in a chemical reaction or chemical equation, you've probably seen it by now, that means it's aqueous. Here we can see an example of what I mean when I say that the particles may give the solution a color even if you can't see them. So on the left-hand side here you have this graduated cylinder, and someone's put some copper sulfate crystals at the bottom of it. Copper sulfate is an ionic compound, and it forms blue crystals. So when you first put it in, it'll sort of fall to the bottom. And you can see there's a little trace amounts of blue in the solution, but most of it has fallen to the bottom. Over time, though, the copper sulfate will dissolve. You can shake it up or stir it to promote this, but even if you just leave it alone, over time the copper sulfate dissolves and you get this uniform blue solution. Okay? When you look at it, you can't see the particles, but you do see that the solution is completely blue. So here we see a chart with some different examples of different types of solutions from solute or solvent particles from all different states of matter. So for instance, if you have a gas and a gas, air is an example of a gas and a gas solution. You have oxygen, about 20% oxygen dissolved into about 70 or 80% nitrogen. Okay? So this can be considered a solution where oxygen is the solute and nitrogen is the solvent. More commonly, we think about solutions as being liquid-based, so you'd have either a gas, a liquid, or a solid dissolved into a liquid. So examples of gas would be soda water or carbonated water, where you have carbon dioxide gas as the solute dissolved into liquid water, or household ammonia, which you might see is ammonia and H3, which on its own is just a gas, but you can dissolve it into water as a solvent. Okay? And then liquid-liquid would be where the solute is a liquid. So in this case, you have acetic acid, which by itself, again, is in the liquid state, but you can also dilute it with water and turn it into a solution, which is what vinegar is. And then there's solids in liquid solutions. So seawater is an example of that, or any kind of salt water where you have salt, solid salt dissolved into liquid water. Or tincture of iodine is slightly different. It's iodine, which is solid crystals, but they are dissolved into alcohol, ethanol. Okay, they don't really dissolve in water that well, so you have to dissolve them in a nonpolar solvent like ethanol. And then the last type is solid and solid. This is a really unusual one. We don't really think of these particularly as solutions usually, but brass can be seen as a solution of small amounts of zinc in a large amount of copper. Right? You can vary the amount of zinc that you dissolve into the copper, and so it'll change the properties of the brass a little bit. Same thing with steel. You can put in a little bit of carbon into iron under a certain process, and it'll turn it into steel, which can be looked at as a solid in solid solution. Water is one of the most common solvents in nature. It's sometimes called the universal solvent because of how prevalent it is in all parts of chemistry. It's a highly polar molecule due to the polar OH bonds. So this we should remember from the section on molecular shapes. You can draw the Lewis diagram for water, and you see that it has two hydrogens attached to an oxygen and then two lone pairs on the oxygen. And so if you consider VSEPR theory, you'll come to the conclusion that it has this bent shape. Okay? And each of these hydrogen-oxygen bonds is going to have a relatively large dipole moment pointing towards the oxygen. And this is also going to be promoted by the lone pairs up here. So there's a lot of negative charge density on the oxygen side. So overall, this molecule has a very large dipole moment pointing from the hydrogen side to the oxygen side. So it's extremely polar. Because these hydrogens are also attached to a very electronegative element like oxygen, this molecule can also form hydrogen bonds. And those are very important in explaining a lot of its unique properties, like its surface tension, its heat of vaporization, things like that. So we can just sort of arbitrarily pick two different substances and try and mix them together and see if they form a solution, okay? But not any two substances will always form a solution, okay? Most of us, I think, have some knowledge of oil and water not mixing, right? So we have salad dressing, for instance, which would be like oil and vinegar, and the two parts separate. Or if there's an oil spill, you'll see the oil on the surface, right? So most of us know that oil and water don't mix, okay? So why don't they mix? Well, the reason is that the intermolecular forces in the oil and in the water are very different. So a solution can only form when you have solute-solvent interactions that are similar to or larger than the solute-solute interactions and the solvent-solvent interactions. Okay? So if the solvent would rather stick to another solvent molecule, then they'll just stick together and they'll exclude any other substances, and so they won't dissolve them. Same thing with the solute. If the solute particles prefer to stick together, if they have strong interactions with one another, then they're not going to break apart into solution. So it's only when the solute particles have a strong enough attraction for the solvent particles that you have a solution form. Okay? And so this leads to a sort of rule of thumb that we have for when two compounds will form a solution, and the phrase is like dissolves like. Okay? And what it means is if you take two substances that have the same polarity, right? So either they're both polar or they're both nonpolar, then a solution will form. Okay? So you have either a polar solute and a polar solvent, or a nonpolar solute with a nonpolar solvent. In both of those cases, it's likely that you'll be able to form a true solution. If the polarities don't match, so if you have a polar solute and a nonpolar solvent, or a nonpolar solute and a polar solvent, then solutions will not form. Okay? The attractions between the solute and the solvent will not be strong enough to promote the uniform dispersion of the solute, and it won't form a solution. Okay? So this is the general rule that you should remember. Like dissolves like. Polar solvents dissolve polar solutes. Nonpolar solvents dissolve nonpolar solutes. So there are really sort of three different types of solutes. You can have polar and nonpolar, which are both the classifications for covalent, but then you can also have ionic solutes. And ionic solutes are really sort of the extreme end of the polar solute classification. So sodium chloride crystals, for instance, will dissolve in water because sodium chloride as an ionic compound is extremely, extremely polar. Okay? It's made up of all positive and negative ions, alternating positive and negative ions. So what happens is if you put a crystal of salt into water, the water molecules will approach it, and the negative oxygen side of the water molecule will be attracted to the positive ion, in this case the sodium, and the partially positive hydrogens will be attracted to the negative ion, which is chloride in this case. And so they'll have strong enough attractions that they'll be able to sort of pull ions out of the crystal lattice and then surround them the way that you see here. Okay? And so they're surrounded such that the opposite charges are interacting. So this is a sodium ion, a positive sodium ion. So the molecules close to it, the molecules of water, are arranged or pointed so that the oxygen side, the negative oxygen side, is directed towards the sodium. Okay? And that allows it to stabilize the charge and stay in solution. Okay? We say that this sodium ion is hydrated. Okay? It's surrounded by a shell of water molecules. Okay? On the other hand, the chloride ion will also be hydrated. It'll also be surrounded by a bunch of water molecules, but they'll be oriented differently. This time the hydrogen sides will all be pointed in towards the chloride. Okay? And this is obviously dynamic. All of these are moving around all the time. It's in a liquid state, so they're moving past one another and going all over the place. But on average, this is how the molecules near the ions are oriented. Okay. And so we can also write this dissolution process as solid sodium chloride, right? The S here means solid. Reacting, not really reacting, but dissolving with water. So we put the water above the arrow, and we show that the sodium chloride breaks apart into sodium ions dissolved in solution and chloride ions dissolved in solution. Okay? So again, this AQ means dissolved in solution, and now we can get a slightly better idea that it actually means hydrated. Okay? It means every atom or ion is surrounded by a cage or a shell of water molecules. The next type of solute is a polar solute, and this refers to a polar covalent or a polar molecular compound. And so polar solutes, as we learned, require polar solvents to dissolve. Okay? A polar solute will form a solution with a polar solvent, but it's unlikely to form a solution with a non-polar solvent. Okay? So this example shows us methanol, which is a polar molecule, dissolving in water, okay? Which we already know is a polar solvent. So methanol has a structure very similar to water. We already saw that water looks like this, oxygen attached to two hydrogens, okay, and has lone pairs. And so this can undergo hydrogen bonding, has a dipole moment, all that. Methanol actually has a structure that's very similar to water. So if you look at this part of methanol, it looks identical to that part of water. The only difference is instead of being another hydrogen on this side, it's a carbon that's attached to three hydrogens. Okay, so this is methanol, and because it has a structure that's very similar to water, it also undergoes hydrogen bonding, and so the attraction between a methanol molecule and a water molecule is pretty significant. Okay, it's at least as strong as it is between two methanols or two waters. And so this allows the methanol to dissolve in water and form, hydrogen, a bunch of hydrogen bonds and a lot of intermolecular forces, and so it will form a true solution. Okay. Nonpolar solutes require nonpolar solvents for a solution to form. So if you have a nonpolar solute like iodine or oil or grease, those are all nonpolar compounds, they're not going to dissolve in water. Okay? And that's because there's really no attraction between the molecules of, say, iodine or oil and a water molecule. There's no hydrogen bonding, there's no dipole-dipole attraction, there's only very, very weak attraction, so the water would really rather stick to itself. The water molecules will all experience strong intermolecular forces between one another, and so they'll sort of exclude the solute particles from dissolving. Okay? And so you can see a striking example of that. This is from the BP oil spill in 2010, where millions of gallons of oil were spilled out of a rig in the Gulf of Mexico, and you could see the oil on the surface of the ocean for months and months and months, probably still can in some places. Okay, so this is the oil here not dissolving into the water. So let's go through a couple of simple conceptual questions. For each of these combinations, identify the solute in each of the solutions. Okay, so if you take 2 grams of sugar and you dissolve it into 100 milliliters of water, which is the solute? Well, this is a classic example. You have a small amount of a solid dissolving into a larger amount of a liquid, so the small amount of the solid is going to be the solute. Okay, so sugar will be the solute here. For B, you have 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol. This 30 milliliters is less, so this would be the solute, the methyl alcohol. Okay. The next one, you have 55 milliliters of water and 1.50 grams of sodium chloride. Again, you're dissolving this small amount of sodium chloride into this larger amount of water, so the sodium chloride is the solute. And then the last one, we actually did this already, but air is a mixture of, say, 200 milliliters of oxygen and 800 milliliters of nitrogen. So the smaller amount is the oxygen, so that is the solute. So which of the following statements about solid lithium chloride dissolving into water are true? You have 4 different statements here. The first is lithium ions are attracted to the oxygen atom of water. Second is lithium ions are attracted to the hydrogen atoms of water. Third is chloride ions are attracted to oxygen atoms of water. And fourth is chloride ions are attracted to hydrogen atom of water. So what are the attractions that form between the ions in lithium chloride and a water molecule? Well, we can see that lithium is positive, right? So lithium, which is a positive ion, is going to be attracted to the negative end of the water molecule, which is the oxygen side. Okay, so this first statement is true. Lithium is attracted to the partially negative oxygen. Okay, lithium is not attracted to the partially positive hydrogen, so this is going to be false. Okay, so this first one is true, second one is false. The third one is negative chloride attracted to negative oxygen. That's also going to be false, right? We're not going to see that because you wouldn't have 2 negatives coming together. But the negative chloride will be attracted to the positive, the partially positive hydrogen side. So this one will be true. So which of the following solutes will dissolve in water? We have sodium sulfate, Na2SO4. We have gasoline. We have iodine, I2, and we have hydrogen chloride, HCl. So the only rule we've learned so far is that like dissolves like, so we should really just look at these and try and determine whether or not they're polar, and if they're polar, they'll probably dissolve in water. So the first example is an ionic compound, sodium sulfate. Ionic compounds tend to be polar, so we can assume that this would dissolve in water. For B, you have gasoline, and they tell you that gasoline is nonpolar. Okay, and that's useful because that tells you that gasoline will not dissolve in water. They have different polarities. The third one is I2, and you have to know something about the polarity of this. So you have to be able to draw the Lewis structure for I2, and even with all of its lone pairs, recognize that it doesn't have a buildup of charge anywhere. It's the negative charge is uniformly distributed. The bond itself is nonpolar, and so this is nonpolar. Okay, which means it's not going to dissolve in water. And HCl, hydrogen chloride, this is not technically an ionic compound because hydrogen is not really a metal, but it does share some very similar properties. It has a very polar bond in it, and so this is a polar covalent molecule which will dissolve in water. Okay, so the only ones that we see that will dissolve in water are A and D. Oftentimes in chemistry, when you're done running a reaction, what you get at the end is a crude mixture of a lot of different things. There'll be side products from other reactions that you didn't really want. There'll be leftover starting material that you don't want, maybe catalysts that you use in the reaction, some solvent that you use that you don't really need. And really what you want to do is isolate the one product that you were looking for from the reaction. So one method to do that, which is frequently used in research chemistry, is a liquid-liquid extraction. What this is you take 2 incompatible liquids, right, one polar and one nonpolar, and you mix your crude mixture into them, and the polar compounds in the mixture will tend to go into the water, and the nonpolar ones will tend to go into the other phase, the nonpolar phase. Okay, so in this case, we have water and dichloromethane. Dichloromethane is a very nonpolar compound, and it's also very dense. So the polarity distinction or difference will keep them from mixing together, and then because dichloromethane is dense, it'll sink to the bottom. Okay, so once you have this mixture, then you can add different materials to it and see which part they go into. So for instance, if we take this mixture and we put in some nickel nitrate, NiNO32, and we mix it together, at first, after you've just mixed it, the whole thing will look like a sort of a muddy green mess because it looks like it's all mixed together, but then it will quickly spontaneously separate back into the 2 phases where you have the water layer on top and the nonpolar organic layer on the bottom. And nickel nitrate, being an ionic compound, which is pretty polar, will dissolve into the water phase, but it won't dissolve into the dichloromethane phase. And so once they separate, all of the nickel nitrate will get dragged along with the water into the top phase. And so you'll see it turn green because that's the characteristic color for this compound. The dichloromethane on the bottom is not going to have any color because it doesn't dissolve any of that ionic compound. Okay, so the polar nickel nitrate goes into the polar layer, the polar partition. Okay, so this allows you to separate based on polarity. On the other hand, if you put in a nonpolar compound like iodine and then you shake it up and let it separate, the iodine this time is not going to go into the water phase because it's not polar, so it's incompatible with the water. Instead, it'll go into the nonpolar organic phase at the bottom, and so you'll end up with all of this purple solute down here. The iodine becomes dissolved solute particles in the nonpolar phase, and it gives it a purple color, whereas the water stays pretty much clear. Okay? There may be a little bit in because you might get traces of iodine in the water, but overall, water is not very effective at dissolving a nonpolar compound like iodine, so it'll all, or 99% of it will go into this nonpolar phase. So you can imagine that this would be pretty efficient if we had, say, a mixture that for some reason had iodine and nickel nitrate. We could just put this mixture into this system here, into this test tube with these two different solvents, mix them up and let them separate, and they'll do the work of separating the compounds for us. All of the nickel nitrate will go to the top, and all of the iodine will go to the bottom, and we'll have separated our different components.